Previous session, we in the previous two sessions we studied about simple stresses, in which we saw uh, simple concepts and introduction about stresses and the strength of material. After that, we saw complex stresses. In complex stresses, we saw a different situation in which uh, a machine element or a machine component or a structural component is subjected to stresses in more than one direction. In it, we saw principal planes, principal stresses, Morse circle, stress transformation, etc. And the same applies for the strain as well. Now, in today's session, we are going to complete, we are going to try to complete these three chapters. The first is bending stress or stresses, or it is also known as stresses in beams, torsion, and strain energy. We are going to cover these three topics today. So, once again, I welcome you and let us just now start this today's session. Bending stress. Let me to understand this concept. Let us assume that we have this bar here, bar, or let's say it's a beam. Okay, so now I have to bend it. So how can I bend it? Should I apply a force, or should I apply a torque or a moment? So for that, let us just look at this example. This is a plain uh, ruler scale that I have here. Now, if I have to bend it, can only applying this force is sufficient for this? So no, it is not bending, but it is displacing. But in order to bend it, what I have to do is I just do it just like this, then it bends. So these two supports are very necessary for bending it. What these supports are doing it, this is a fixed support here, and then I apply a force down here. So what this, there is this perpendicular force and this distance. So distance into the perpendicular force or force into the perpendicular distance is your moment. So one thing is clear, that to bend a beam or rod, we require bending moment. We just apply a moment, and the moment which bends this beam is known as bending moment. So to this bar, let us say I applied a moment M. So this is how it will bend. So I will draw it here. So this is how the beam is bent. This is the radius of curvature. This is the centroidal axis. If you can just pay close attention to this bent beam, you will see that this portion, or the top fibers which are about this axis, which is also known as neutral axis. Now this portion is under tension. whereas this portion is in compression. No, you can see here it is a stretching kind of action. The fibers are getting stretched, whereas in the downward position you can see that here the elements are getting compressed. So if I have to draw stress distribution diagram, then it should be something like, wait a minute, let me draw. Okay, so this line is our neutral axis, and above the neutral axis what we are what our uh, members or say layers are experiencing is a tensile force. So to the positive side it will be tensile, and to the negative side it will be compressive stress. So let us draw stress distribution. Sigma b, this is bending stress, this is also sigma b. The magnitude of both the sides are going to remain same. Okay, so this sigma b is bending stress. Okay, so now it is known that the sigma b is a direct stress. It is a direct stress. It is not shear stress. Okay, so now let us see how the equation. What is the equation to find this? Because I will describe the other things later, and to find this bending stress, we have this equation sigma b by y equal to m by I, sorry, m by I equals to E by R. Now, interesting thing here is sigma b is bending stress. Now, y is the distance of your layer from the neutral axis. I is moment of inertia in mm to the power 4, area moment of inertia. E is modulus of elasticity, and R is the radius of curvature. R is the radius of curvature. Now, if we keep all this thing, if keeping all this thing constant, if we try to keep all these things constant, then we can write sigma b by y equal to m by I. Now, for this thing to be constant, we can say sigma b is directly proportional to y. So this equation means that as the distance of the layer, there are this beam of yours. Let me draw in an enlarged view. This beam of yours is made up of layers. These are the layers. These are layers, and this is our neutral axis. So each layer has a certain distance from neutral axis y, let's say y1, y2, etc. So as the distance from neutral axis increases, the stress also increases. So let me now complete this diagram. Okay. Now This is how it works. Now, similarly, we can also make an observation that in this equation, if y equals to 0, sigma b equals to m by I into 0, then it implies sigma b will also equals to 0. That is at y equals to 0, which means at neutral axis, the bending stress is 0. See, so here the bending stress has a value 0. So this is how the stress distribution works. Now, if I have to draw stress elements for the top fiber and bottom fiber, then it will look like something. For top fiber and for bottom fiber. For top fiber, it is in tension, and for bottom fiber, it is in compression. So I hope this thing is clear to you now. Okay, how bending stress works and uh, what what are various observations that can be taken from it. Okay, so now if let's say, let us discuss a scenario of a problem which you can solve easily by using the similarity of triangle. Okay, so now you have given the value of stress, the maximum permissible stress sigma b max, and also the value y max. It is, let's say, it is a rectangular beam. This rectangular beam has been subjected to the bending stress. Now it has this distance h by 2, because its total height is h, and this is h by 2. So this is y max. This is the maximum distance of the top layer. It is the distance of the topmost layer from the neutral axis. Okay, so this is neutral axis, and from the distance of the topmost layer is y max. So at that top layer, top at the toppest level, the stress will be maximum. Now, if let's say at a distance a, you have to find the value of sigma b, the bending stress here. So how you will find? You will just take these two triangles into consideration: O A B, O B, sorry, O C D. From the similarity of triangle, you have uh, this angle of 90 degree. This side, this side is almost similar, and this angle is common to both, as well as this angle is also same. So by angle traced, we can say that triangle OAB and triangle OCD are, not B, it's D, are similar. So in this case, what we can do is we can use this property of triangle. We can write OA upon OC is equals to OB upon, sorry, AB upon PD. Now what is OA? from O to A distance is small a. From O to C, the distance in is y max. What is AB? AB is what you have to find, bending stress. And what is CD? CD is sigma B maximum. So sigma B will be equals to sigma B max multiplied by A upon Y max. So by using this simple property of the simple concept of similarity of triangles, we can find this the bending stress at any given layer. Okay. Now one more concept we have to see before moving to our next chapter is yes. Now this topic is shear stresses in beam. Consider cantilever beam. Okay, this cantilever beam is subjected to a force P. What this force will cause if the length of this beam is L, then it will just look at the scale again. Now, if I apply a force here right now, so what it will do, it will just bend it because it is a support here and a distance. So distance, sorry, the force multiplied by perpendicular distance is a moment. So there is a bending moment which caused the beam to bend. So the first stress that will occur in it is the bending stress. What is the reason of this bending stress? The bending moment is causing it. The other stress that will be present in this beam will be a shear stress. How? Because I told you that when you have to cut a cake, the cake get cuts along the line of application of force. The other stress is your shear stress, because if this has to be applied somewhere, let's say it is not uh, exactly at the this force, sorry, let it be there. So yes, so this is the force, and this is the parallel area which is parallel to it. So the other stress uh, that this beam will be subjected to is shear stress. Okay. So now we have bending stress that we just saw it, just that we just saw in the earlier section. How to find that bending stress? It is very easy. We just have to use this equation, sigma b by y equals to m by I equals to E by R. Fine. So now how to find this shear stress? It is, and now this is how, now in this session we will, in this section we will see how to find the shear stress. So let us say this is some beam of arbitrary shape. This is the cross section of the beam. This is your neutral axis, and V is your shear force. The width of this cross section is B. Y is the distance of this bottom layer from the neutral axis, and y bar is the distance of the centroid of this area from the neutral axis. Now the shear stress acting on this cross section is given by tau equals to V. mm, Wait a minute, I just need to. Tau equals to V A y bar upon I into B. I is moment of inertia, A is this cross section area, y bar is the distance of the centroid from neutral axis, and V is the shear force. So this is how you can find the shear stresses in the beam. Now let us look at some standard cross sections that we come across. Fine. So let us see what will happen if we have a rectangular cross section. Now this is the neutral axis as well as centroidal axis. The centroid and the neutral axis coincide with each other. And this beam has been subjected to a shear force V. Now average shear stress is is shear force acting upon total area is V by A. But the intensity of shear stress varies with the distance from neutral axis. So let me draw a stress distribution diagram for this. Yes. So this is where the shear stress will be maximum, and here the shear stress will be 0. This is how shear stress varies for a rectangular cross section. Okay, this is tau average and this is V by A. So we can say the it is. I will not just go into the derivation part, but the maximum value of this shear stress is equals to 1.5 times the value of average shear stress. Now, for beam with a circular cross section, the neutral axis will again pass through the center. Here also, the shear stress varies, and the shear stress will be maximum at the neutral axis. And the value of shear stress, the maximum shear stress is 1.33 times tau average. Yes. Now, what is a triangular beam? And we don't come across triangular beams, but it is an interesting cross section. Why, I will just tell you it in a moment. Now, the neutral axis here, this is the neutral axis, but the maximum shear stress is not on the neutral axis. It is somewhere above the neutral axis. So the stress distribution diagram, if I may draw it, it is something like this. So here you will have tau max. So tau max for triangle is 1.5 times tau average, and shear stress at neutral axis is equals to 1.33 times tau average. So this is for a beam with a triangular cross section. Fine. So let us just revisit these things that we studied right now. That let us get back to this diagram of our beam. This beam is subjected to load P. Because of this loading, there will be two effects. There will be two effects of this loading. One is bending, the other is shearing. Now, why I am telling you all this? Bending and shearing. What is it? What is it used for? What is its use to us? The one thing is that when we see a beam like this, we have to we know that it may fail in bending as well as shearing. ये बेंड होकर भी फेल होगा, या बेंड होकर भी टूटेगा, या ये shear होकर भी टूटेगा. shear मतलब कट जाना. अब बेंडिंग में भी ये बेंड हो सकता है. तो हमारा काम ये है कि ना इसे बेंडिंग में टूटने देना है, ना शेयरिंग में टूटने देना है. So we have to save them from these two stresses. We have to make sure that these two stresses stay within the limit. So for this, we had this formula: sigma b by y equals to m by I equals to E by R. इस फॉर्मूले से हम बेंडिंग स्ट्रेस का पता कर सकते हैं कि कितना बेंडिंग स्ट्रेस आ रहा है, और उस बेंडिंग स्ट्रेस को परमिसिबल लिमिट के अंदर रखने के लिए हम यहाँ पर पैरामीटर्स में चेंज कर सकते हैं, मोमेंट ऑफ इनर्शिया में और द एंड द क्रॉस सेक्शन ऑल्सो. द अदर थिंग इज शेयरिंग. So the shear, to find shear stress, I told you this formula VA y bar upon I into B. So we can also take care of shear stress, and we can make our beam stronger, and so that it will not fail either in bending or shearing. Now this is clear that we have to save our beam for bending as well as shearing by using this formula. Now I am sharing some important points here with you regarding bending stress. Now you know that sigma is directly proportional to E, and sigma is equals to sigma, the stress is directly proportional to strain as per Hooke's law, and it is epsilon into E. Fine. Now from this equation you can see sigma b by y equals to E by R. This is what I can write. So sigma b equals to y by R into E. Now this is a direct stress, and this was also direct stress. So y by R into E becomes your strain. So the strain in the beam, the strain in beam can be found by y by R. The strain is a dimensionless property, it does not have any unit. Similarly, y by R is the ratio of two lengths or distances, hence it also have no unit. So this is how you can find strain in the beam. The other thing is about section modulus. Now section modulus is denoted by term Z, and it is the ratio of the moment of inertia and the distance from neutral axis. Z equals to I by Y. So for a rectangular beam, suppose we have a rectangular beam with a rectangular cross section, which has a width b and height h. For this, z will be, what is a moment of inertia for rectangle? It is bh cube by 12, and the distance from the neutral axis will become h by 2, divided by h by 2. So what the section modulus for this beam will be bh square by 6. Now this section modulus is very important in finding the strength of the beam. बीम में कितनी ताकत है ये उसके क्रॉस सेक्शन से डिफाइन होगा, और उस क्रॉस सेक्शन की एक प्रॉपर्टी जो है, उस क्रॉस सेक्शन के लिए एक पैरामीटर है सेक्शन मॉड्यूलस z. So you have to make sure that if you have to make any changes within the beam, you have to consider this section modulus. So the sigma b, from this equation I can write sigma b by y equals to m by I. Now I can just rearrange it and I can write m by I by y. I will send y here. So sigma b equals to m by z. So this becomes our equation for bending stress. Now this was all about the stresses in beams. Now let us move to the next chapter, that is known as torsion. Once again, we have this shaft here. This shaft also has layers to it. Fine. Okay. Now the condition of our shaft is like this. If you are able to see this paper, let me just if you can have a look at this paper has the lines over it which are equivalent to the layers that I showed you. Okay, so if I have to twist this, if it is not visible, okay, now these layers are visible to you guys. Now what I will do, I will just twist it. So yeah, I applied this twisting moment and see what has happened to the layers. The layers are now inclined. Okay, the layers are getting inclined. If you can see here, just try it with yourself, with your paper, yourself as of your own. You will find the layers get inclined. Now wait a minute, where's the screen? Okay, I hope the screen is visible now. Yes. Okay, so as I told you, the now the layers will get inclined. How it will get inclined, or why it will get inclined? Because I applied a twisting moment or torque to this uh, shaft. So the diagram here, the lines are parallel. If you get and see that paper of yours, so this angle made by this the angle by which uh, this layers get inclined is known as angle of twist. Angle of twist. And T is torsion. Now, if let us say L is the length of this shaft, then the twisting moment can be found out by using this formula T by J equals to tau by R equals to G theta by L, where G is modulus of rigidity. So this is how we can find torsion. Now, how is the stress distribution given for this shaft? It is like this. Tau, and at the outermost layer, the shear stress uh, will be maximum. Why? Because let us see why it is so. T by J equals to tau by R. If these two terms are constant, then tau is directly proportional to R. At R equals to 0, shear stress also is equals to 0. And at if R is maximum, then tau is also, and let me just rewrite it. So from this equation, we can write tau is directly proportional to R. Now there are several conditions at R equals to 0, tau equals to 0. If R is maximum, then tau will also be maximum because they are in direct proportionality relationship. So this is why the stress distribution looks like this. It is a radial phenomenon. Now if I have to draw stress element, if I have to draw stress element, the stress element for this outer fiber, only shear stress is acting on this shaft. So tau, tau, that is shear stress. So this is how the stress element looks for a shaft under torsion. At the center there is no stress, so there will be there we cannot draw a stress element there, because even if we draw a stress element, it will be just a rectangle without any stress acting on it. Let us just now move forward and see different conditions for a circular shaft. So this is a shaft here. A shaft has a circular cross section. Shaft has a diameter d, so this distance will become d by 2. So if I have to find the shear, the twisting moment, then T by J equals to tau by R. Now J is polar moment of inertia. J is polar moment of inertia. So I can write J equals to pi by 32 d to the power 4. So this is the equation of polar moment of inertia for the circular shaft, for a circular cross section. So we can write, and R can be, the radius can be written as d by 2. Putting these two value in this equation, we can get this equation. T is equals to pi by 16 tau d cube. Now this is how we can get the twisting moment as well as the torsional shear stress. The tau is what? Tau is torsional shear stress. Okay. So this was the case when this shaft was only subjected to the torsion, only to the twisting moment. I just draw it at, yes, twisting moment. The action is like this. Now, if this shaft is subject, what will happen if this shaft is subjected to the bending moment as well? Shaft subjected to bending moment. Now the same shaft is subjected to bending moment M. We know that for bending we have equation sigma b by y equals to m by I equals to e by r, which we do not require at this time. M is bending moment. I is what? I is your moment of inertia. So for a circular shaft with diameter d, the diameter here is d, the moment of inertia is pi by 64 d to the power 4, and y, which is the distance from the neutral axis, the maximum distance from from the neutral axis will be d by 2. So y will be equal to d by 2. Putting these two values in this equation, we can find the bending moment is given by pi by 32 sigma b into d cube. So this equation is for when shaft is subjected to bending moment, and when the shaft is subjected to twisting moment only, shaft subjected to twisting moment only. So here we have this equation for only twisting moment, and here we have this equation for only bending moment, when the shaft is subjected to only bending moment. Now there is a third and interesting condition where the shaft is subjected to both of these kind of stresses, the both of these moments. The shaft is subjected to bending and twisting moments simultaneously. Bending moment is your M and twisting moment is T. So let me draw this diagram. So this will be your bending moment M, and this will be your twisting moment T. Fine. So if this both of these moments are applied, then how how should we design this shaft then? If a shaft has to be designed for bending moment as well as the twisting moment. See, if the main task of the shaft is to rotate. So a motor, whenever it will be coupled to a motor, the motor will transmit the torque to this shaft. So we have to definitely design it for torque. Now, if there are some mountings of this on this shaft, such as flywheel and other mountings, coupling flywheel, then that the weight of that mounting will cause a bending moment on this shaft. So we have to design it for both bending moment as well as twisting moment. So how can we define, how can we design? To design it, we have two theories of failure. That the first theory says that it will fail purely due to bending stress. Failure will be caused by bending stress. The second theory says that the failure will be caused by torsional shear stress. Now, this theory is backed by a theory of failure known as maximum principal stress theory, and this theory is backed by maximum shear stress theory. तो इसका मतलब है कि दो कॉजेस ऑफ फेल्योर है, या तो ये बेंडिंग स्ट्रेस के वजह से टूटेगा जो कि एक नॉर्मल स्ट्रेस है जो प्रिंसिपल स्ट्रेस के अंदर आएगा, या तो ये शियर स्ट्रेस के वजह से टूटेगा। तो शियर स्ट्रेस की वजह से अगर टूटेगा तो हमें मैक्सिमम शियर स्ट्रेस थ्योरी को यूज करना है। सो लेट अस सी व्हाट दिस टू थ्योरीज हैव टू से। मैक्सिमम प्रिंसिपल स्ट्रेस theory. According to maximum principal stress theory, the sole responsible factor for the failure of this shaft is your bending stress. Bending stress is going to damage your shaft. So now we have to find the value of this maximum bending stress. How we can find it? We have to find an equivalent bending moment, because there are two moments acting now. One is M and other is One is M. Let me just draw that diagram here. Okay. So here we have bending moment M and twisting moment E. Because there are these two moments, then we have to find an equivalent moment, and then it will be equated with pi by 32 sigma b max into d cube. So this is what is going to help us. Now, how to find this equivalent moment is by this equation. The equivalent moment is half m plus under root of m square plus t square. Now, similarly, the maximum shear stress theory tells us that the sole responsible factor for the failure of your shaft is the shear stress only. So what we are going to do is we will just equate with a equivalent twisting moment, and the formula for twisting moment is pi by 16 tau d cube, but here it will be the maximum shear stress. Now this equivalent shear stress is equals to under root of m square plus t square. So this is how we have to find the values of the diameter from both of these equations. Let us say this value is from the bending moment, so I am writing m, and this is uh, the value from the twisting moment equation. The greater the value, maximum out of dm and dt, the value which is greater is is taken as the diameter of shaft. So in that way, our shaft becomes safe and it will not fail. So we have to compare these two diameters. In the problem, in the question, they are going to they are going to just ask you specifically about, they will mention the theory of failure or according to which you have to calculate and find the diameter of your shaft. Most of the time it is maximum shear stress theory, so go with this theory. Okay, if it is not mentioned, then go with maximum shear stress theory. But if they are mentioning it in the problem that maximum there is a maximum principal stress theory, then use this formula. First find equivalent bending moment, then equate, then put the values into this equation, and you will find the value of your diameter of the shaft. So this was all the discussion about torsion as well as the uh, stresses in B. Now we are going to look to the next chapter, which is of strain energy. Okay. So this is a rod subjected to a load P. What happened to this rod is it got elongated because of this force. This deformation is dl. Its original length was L. Now what I did was, the load was applied gradually. So let me draw a chart for it, a graph for it. I went on increasing. The load reached a value P, and on this we have deformation. Here we have load, and here on this side we have elongation. And at this point, the deformation was dl. Now, what happens when a material gets deformed or elongated is that under the action of that load, it gets deformed and it stores some energy within it. It uses that energy to regain its original shape whenever that force is removed. So this energy is known as strain energy. So whenever uh, an object is strained or deformed, it stores some energy. It uses that energy to regain its original shape whenever the load is removed. I hope the concept of this energy is clear, and this energy is nothing but strain energy. So strain energy is denoted by U, capital U. Now we know that by first law of thermodynamics, which is a universal law, it is applied on all of these all of the in on all the subjects you are going to study. It states that energy and work are mutually interconvertible. So we know that the strain energy is equal to work done. If you have to find the work done, then you have to find the area under this curve. This is load into this is the displacement. So the area under this curve is half into P into dl. But we also know that dl is given by PL upon AE. So I can write now the half will come as it is. Now this load P can be written as stress into area, and this P by A can be written as sigma, and then say that means the stress into L by E. So ultimately this equation will become sigma square upon 2E multiplied by area, cross section area into the length. Now cross sectional area into the length becomes volume. So sigma square upon 2E multiplied by volume. This is the equation for the strain energy. So this equation is pretty much useful in finding this strain energy. Now there is an additional terminology that I want you guys to remember, which may get asked into fill in the blanks type of questions. Okay. So there is a terminology known as proof resilience. Now resilience is nothing but a maximum, it is the maximum. So let us get let us have a look at this stress strain diagram. Fine. This is our stress strain diagram. This is stress and this is your strain. This is somewhere here lies your elastic limit, and the maximum strain energy stored within the elastic limit is known as proof resilience. So the proof resilience is, I will write it PR is equals to maximum strain energy. Now we have this equation sigma square upon 2E into volume. This is what we derived. I can also write it as sigma by 2 into sigma by E into volume. Now stress upon modulus of elasticity is what is your linear stress into volume. So this is your proof resilience. Now there is another term known as modulus of resilience, which is very easy. Modulus of resilience. Modulus of resilience is denoted by small u, and it is nothing but the proof resilience divided by volume. So if we divide this by the volume, then what we have remaining here is half into stress into strain. So it is nothing but the maximum strain energy stored within the elastic limit per unit volume. Per unit volume. That is the main difference between proof resilience and modulus of resilience. So this thing may get asked in your examination for 1 mark. Okay, this difference. So let us now end this session by summarizing today the topics that we saw today. So we saw 3 topics today. The first one of it was stresses in beam. Very easy to remember it is. Suppose that we have a beam which is subjected to a load P, then there are 2 modes in which this beam is going to break. So I beg a pardon, and now I will going to use Hindi only so that we can summarize this so easily. तो बीम जो है आपकी ये 2 तरीके से फेल होगी, एक आपके बेंडिंग में और दूसरा आपके शेयरिंग में. अगर बेंडिंग में इसको बचाना है तो हमारे पास फॉर्मूला है सिग्मा बी बाय वाई इक्वल्स टू एम बाय आई इक्वल्स टू ई बाय आर. और अगर शेयरिंग में इसको बचाना है तो हमारे पास फॉर्मूला है टाउ टू वी ए वाई बार अपॉन आई इंटू पी. ये सारे दोनों इक्वेशंस को आप वापस से अपने वीडियो को रिवाइंड कीजिए और ये दोनों इक्वेशंस के बारे में मैंने जो बताया वो आप इनको वापस से पता कर सकते हैं. So this is how the stress. This is how a beam may get failed. So and there was this stress distribution diagram for the bending. There was a neutral axis. Again there is an important point. एक important point बताया था कि neutral axis पे stress की value 0 होती है. Okay. This is how the stress distribution was. Then the second topic that we saw was of torsion. Torsion. तो इसमें हमारा एक shaft होता है. The shaft को ऊपर ट्विस्टिंग मोमेंट अप्लाई होता है एंड बिकॉज ऑफ दैट मोमेंट वजह से ये टूट सकता है. इस इक्वेशन से हम फाइंड आउट कर सकते हैं उस shear stress की वैल्यू, द मैक्सिमम shear stress की वैल्यू दैट इज इंड्यूस्ड इन योर शाफ्ट. देन वी सॉ इसी के अंदर फिर हमने 3 कंडीशन देखी थी. शाफ्ट subjected to bending only, shaft subjected to torsion only, and shaft subjected to bending and twisting as well, torsion simultaneously. So this is what we saw in the section of torsion, and finally we saw about strain energy, a brief concept about strain energy. व्हाट इज दिस स्ट्रेन एनर्जी? स्ट्रेन एनर्जी क्या होता है? जब भी आप किसी मटेरियल को डिफॉर्म करोगे तो वो एक एनर्जी स्टोर करेगा, उस एनर्जी को वो यूज करेगा अपने शेप को रिगेन करने के लिए जब लोड को आप हटा देंगे। So that energy is known as strain energy. And the formula for strain energy was sigma square upon 2E into volume, or half into sigma into epsilon into volume. Then there were two concepts in addition to it. One was proof resilience and the other was your modulus of resistance, modulus of resilience. It was small u, which was half into sigma max into epsilon. So this is it for today's session. We completed these three sections today. The subject itself is vast, and I am trying my best to compress it and provide you the most important informations that are required for solving the paper in the gate. So thank you very much. We will meet in the next session and will try to complete this subject.